Pelliciari, so I'm sorry if I'm speaking wrong pronunciation. He is going to talk about investigating the FRB-magnetar connection by monitoring observations. So this is a contributor talk. So David, so please start when you are ready.
Okay. Hi everybody, my name is Davide Pelliciari. I'm a PhD student from the University of Bologna, and I want to thank the organizers for giving me this opportunity to present today my work. And today I'm going to present the results from a long monitoring on nearby galaxies conducted with the Northern Cross Radio Telescope with the aim of investigating the FRB-magnetar connection. So let me start by saying a few words about the Northern Cross. It is this very nice T-shaped radio interferometer located in Medicina, very close to Bologna, in which I live. And it is composed of two arms, the north-south arm and the east-west arm. And but the latter is out of service. It is actually under development. And we used for our observations 8 cylinders of the north-south arm, because the focal line of 8 cylinders have been recently refurbished in order to group the signal of 16 dipoles together to form 4 analog signals per cylinder, and we from different cylinders in order to form a steering electronic beam in the sky to track the transit of a source over the Northern Cross Radio Telescope. We work at a central frequency of 408 megahertz in a bandwidth of 16 megahertz with resolutions, so spectral resolution 14 kilohertz and a sampling time of 138 microseconds. So in these years, the Northern Cross FRB project has been focused on the monitoring of the most active repeaters, as reported in the work of Matteo Trudu et al. 2022, in which we observed and report a long monitoring on 4 active repeaters, and among of them we collected 3 bursts from FRB 180916, and which are displayed up here, and from them we continuously monitor this source in its periodic activity windows, with the aim also of doing multi-wavelength observations, so in synergy with Agile and Swift X-ray instruments. And during the observational campaign on nearby galaxies, which I'm going to present to you in a bit, we collected other 2 bursts from the same source. So during my first PhD year, I was focused on this nearby galaxy campaign project, in which we observed 7 nearby galaxies located at a distance of within a distance of 12 megaparsec, and we chose them to be star forming, so with reported star formation rate higher with respect to the Milky Way. And we collected a total of approximately 700 hours on them of effective on-source time, and we search FRBs on our observations in a DM range of 0 to 1000 parsec over centimeter cube with less than 35 milliseconds. And the aim of this observational campaign is to, let's say, probe the magnetar burst rate, because from our detection or non-detections, we can place an upper limit on the magnetar burst rate, as I'm going to show to you in a bit. So about the magnetar formation, the FRB magnetar connection, we know that magnetars can emit FRBs, and this is known from 2020, where there was this detection from STEP 2 and Chime FRB of the first FRB-like signal from a galactic source, a galactic magnetar. And so the question now is whether SGR 1935-like magnetars, so like the galactic one, which is probably a core collapse supernova magnetar, can explain the entire cosmological FRB population? And the answer is that yes, it can from an energetically point of view. Indeed, if we consider giant flares from galactic magnetars with the same radio efficiency as SGR-1935, these giant flares can power also even the most powerful FRB, as you can see in this plot from Margalit 2020. But this is no longer true for its repetition rate. Indeed, the repetition rate of SGR-1935 is orders of magnitude lower with respect to the most active repeaters. And so a single population of magnetars like SGR-1935 cannot explain the repetition rate of cosmological FRBs. And Margalit, in its work, proposed to add a second, more rare and more active magnetar population in order to, and in this case, they succeed in reproduce the cosmological FRB population. So FRBs have also been localized in different host environments, and so it is not so trivial to assess the progenitor underlying of FRBs, which is, of course, still unknown. And some FRBs have been associated with late star-forming galaxies. So magnetars, core-collapsed magnetars, can be thought of the consistent with these hosts among other progenitors, of course. But others have been associated with older cell population. And the key example here is the repeater as localized in a globular cluster of the nearby galaxy M81. So for this repeater, some exotic magnetar formation channels have been proposed. Like, for example, the compact merger of white dwarfs or the accretion-induced collapse. So overall, monitoring nearby galaxies can be a prominent tool, a prominent probe to investigate magnetar formation channels, even the most exotic ones. So talking about the magnetar burst rate, as I said, from our observations, we can place an upper limit on magnetar burst rate, and in the literature, there have been two previous limits on these rates, and the first comment came from Chang 2020, who can place an upper limit for a lower limit, sorry, for the magnetar SGR-1935 light burst rate of 0.007, and it came from the detection of SGR-1935. And they placed an upper limit of 0.4 here to the power of -1 per magnetar, and this came from the observation of 15 nearby galaxies, as you can see here from China 2020, and still 2 from the detection of SGR-1935 placed a consistent but broader upper limit on the magnetar burst rate. So regarding our observational strategy for our nearby galaxy campaign, we observed each galaxy during its transit, and since our acquisition system cannot, from our acquisition system, it is not possible to track continuously a source during its transit, we consider a shift and track strategy in which we placed 7 delay beams in our field of view in order to cover the field of view, and so we can track the source as it passes over the Northern Cross array. So as you can see, there is 40% of less response at -3 angular separation from transit with respect to transit. And we took into account this by dividing the threshold, the fluence threshold, which is 38 Jansky millisecond at the peak, at the central peak, by the gain level in the jth beam. So the energy detection threshold for a burst coming from a galaxy placed at distance di is has been calculated in this way. So during our observational campaign, we observed 7 galaxies, and we obtained one detection from a one-off FRB in the direction of M11. But we consider, however, this FRB as coming from beyond M101 because this burst, which has a duration of approximately 2 milliseconds and a fluence of 60 joules per millisecond, have a dispersion measure which is kind of high for being originated from M101, and because the implied DM host, considering an intergalactic medium, yes, thank you, an intergalactic medium negligible is 220 parsec over centimeter cube. So we assess that the maximum luminosity distance for this FRB is 870 megaparsec, and so we consider no detections from our sample of galaxies. So we compute our the expected total burst rate from our sample of galaxy by averaging over the time spent in each delay beam for each galaxy, where in this case R is the expected burst rate from the single galaxy, and we computed by scaling the number of magnetars living in that galaxy by the star formation rate of the Milky Way and the number of magnetars living in our galaxy, and we modulated for a energy distribution function. Here the Heaviside step function restricts the case to SGR-1935 burst. So the main result of my work is that we can place an upper limit on the total burst rate of 38 here to the power of -1, and this translates to a upper limit on the lambda man of 0.45 magnetar -1 here -1. So by considering our observations combined with observations of Chime, we can place an even more stringent upper limit which is the most stringent upper limit to date on the magnetar burst rate, which is 0.25 magnetar to the power of -1 here to the powers of -1. So here I conclude. So we conducted a very long monitoring on 7 nearby galaxies, and we report a single detection of one burst coming from, yes, okay. So these are my conclusions. Thanks for the attention.
Okay, thank you very much for part of the timing. So any questions from the local audience? Shoulder, please.
Thank you, David, for nice talk. I may have missed something. Maybe could you go back to the energy function?
Yes.
Yeah, when you say energy function magnetar, this is kind of X-ray energy or radio energy? Which are you
talking about? Radio energy, yes.
X-ray energy?
No, radio energy.
Radio energy, okay, thanks. Okay.
Yes.
So is there any kind of reasonable measurement of this slope and also the minimum energy, E0? What kind of information do we have already?
Okay, so the gamma have been constrained to be less than 0.15 from the work of Chime 2020, the work of the detection on SGR-1935. So we know that can be steeper than 0.15, minus 0.15. Regarding the minimum energy, we considered our detection threshold for the minimum energy of bursts, and but we consider also the minimum energy of the SGR-1935 burst, which is 4 times 10 to the power of 34 erg as the isotropic energy of SGR-1935. So when our minimum detection threshold is higher than this E0, the energy of SGR, we consider E0 as our minimum threshold.
Okay, thanks. So you're considering only kind of FRB level energy, right? So above the 10 to the 34 L, which is close to the galactic one. So you don't consider below this energy. Okay. Yeah, it's not clear. Thanks.
Thank you very much.
Okay, thank you very much. It's time to move on next talk. So let's thank the speaker again.